So I will talk today about something a bit different from the other talks because my work is pure experimental, so I will not talk about theory and dynamics, but I hope you will find it interesting. So far, a lot of laboratory work was done studying hypervelocity collisions, but the main subject of the study was the target, not the projectile. So there were a different combination of materials. They studied the size and speed distribution of the ejecta, and also when we start to have catastrophic collisions in different combinations of materials. But until now, if you search also in bibliography, you will not find enough information of what is going on with the projectile, the smaller, body of the collision. So that is what we are interested in, because the recent years we saw, for example, that it was found that material on Vestra or on Tokava, or we see this different composition of the meteorites that they came from the asteroid 2008 TC3. So we want to see what's going on, if there is mass from the projectile and how much is it, and it is embedded on the target, if we have large fragments that they survive from the hypervelocity collisions and so on. So that's the aim of our project. So, in our lab, we have two states like the gas gun. Probably some people from here, you're aware of this gun. So we can do low speed but also hypervelocity collisions with this gun. We put it's a simple configuration. We just change the gunpowder and the pressure inside the gun in order to achieve the required speed for the impact. So at the back, you can see the chamber. It was made by NASA, and it was given to us. So the target is placed there. It is under vacuum, and the projectile is placed on this barrel, in the beginning of this barrel, and it is accelerated. And with two different lasers, we can have a very good estimation of the speed of the collision. So we can do a large range of collisions from a few hundred meters per second until 7.5 kilometers per second, but it depends on the type of the projectile and how big, and the size, of course, of the projectile. Generally, we can fire, we can use as targets many materials. We don't have restrictions. We are one of the, there are not many guns this time that they can fire on ice, because we have evaporation, so they cannot keep the pressure in good limits, but we can do it, and also we can use as projectiles different materials, and also we are allowed from health and safety from UK, the bureaucracy. We can also use living creatures, for example, like tardigrades, and fire them, and see, for example, a colleague does this work. It's, for example, from the shock they will alive, who is trying to study the prosperity and all these things. So, yeah, we can do it. We can, originally the file says you can fire everything that doesn't have a spine. If something has a spine, it's not good. Moral ethics, Okay. So, okay, I will continue. So the project is that we are trying to simulate in the lab collisions by using different combination of materials for the target and for the projectile, using also several speeds. I will tell you exactly these are my speeds. So we want to estimate how much mass is embedded on the target, generally not only in the bottom of the crater, and also try to measure the size distribution of the ejecta. And excuse me, if from now on I refer to the ejecta, I mean the ejecta that is from projectiles, because the terms now are reversed. Until now they were used for target, but everything that we say is for the projectile. And also to examine the state of the bigger fragments that they were survived and they were found in the ejecta, again from the projectile. So to give a summary, the first part of my experiment, I used porous water ice. It is a cylinder, and as a projectile I used a 3mm magnesium-rich peridot. It is an olivine with this specific formula. It's magnesium-rich, and we use it. We selected it for a specific reason that I will show you later, because it was going to be very easy for us to identify it later in the ejecta. And this is the range of speeds that I tried to do at the beginning. So the gun. So the projectile travels all the way down the gun, exits here in the chamber, and then it has to pass through this cylinder which is full of ice but with a small hole in the middle. All these funnels have two different setups. They're both full of ice, and then the result, this will be aligned, the door will be closed. Of course, it will be like this, but you cannot see very well. Anyway, so these are aligned, so the projectile will travel in the chamber through the ejector collector, and then will crash on the target, and all the ejector, not all the ejector, the majority of the ejector will be gathered in this area. So it is very simple setup. So let's start with the source. So the first source that I try to do, I try to do 0.5 kilometers per second, but it is not hypervelocity, it is low speed. So the gun cannot be very, very accurate in low speeds. That's why we resulted in almost 0.4 kilometers per second. So the result was that although we have a crater, as you can see clearly here, we didn't miss anything from the projectiles. So this is the peridot. I forgot to say that the peridot that we can find easily is gem. It's like a diamond. It's for jewelry, I mean. It's very beautiful. So it survived completely. Actually, it just bounced on the target, and it was ejected almost with very, very small angles, actually, from the target. So it survived completely. So the second shot tried to be around 1 kilometer per second. Still, it's a bit less, but it's okay. And so exactly the same type of projectile. As you can see here, it crashed from the long, not from the big face, but from the wide axis, if I can say that. It was hit as it was flying in the chamber, and we tried to collect almost 65% of the initial mass and more. And I say more because as I tried to collect it from the chamber, I lost some chips on the way. So at least 65% was rescued. So let's continue. These are two shots around 2 kilometers per second. This is the result. This is the ejector from the ice, but we don't have the ejector from the target. These are some big fragments that survived from this shot, and these are the big fragments that survived from this shot. I will show you this fragment and this fragment. The long axis is about 1 millimeter, so it is comparable with the initial projectile. So, okay, here you can see in zoom, and if you notice this lines here, I don't know if you can see. I hope you can see. This is the shock of the impact. It is something that we didn't see in the previous shots, for example, of 1 kilometer, of 0.4 kilometer. So now that we went to higher speeds, we start to see changes on the projectile. So, okay, 3 kilometers, 3.5 kilometers, both successful, but I couldn't find any big fragments comparable to the previous one, I mean, to be a few percent of the initial mass. We have only very, very tiny fragments. So, some unsuccessful shots. I tried to repeat the 3 kilometers per second, but it went off axis. So it hit exactly the setup, the ejector collector, so it was missed. 0.6, it disappeared somewhere inside the gun. Probably 5 years from now, if our technician opens the gun, we'll find my peridot uncut somewhere there. I don't know where is it. We just lost it. Anyway, it went off axis, but inside the gun. And I tried to push the gun and fire my peridot 2 times, 4 kilometers per second. In both of these cases, it went off axis. The first case, it crashed inside the barrel of the gun. The second time, it crashed here, where it exits the gun and enters the chamber of the target. And this is a combination of high velocity and also very strange symmetry of the gem projectile. So I don't know if we can go to higher speeds with this specific projectile. So, the analysis. After we do the shots, we result with 2 big portions of ice. So what we do, very simple, we just melt the ice. And after we melt the ice, we just filter the water. So in one filter, we result with the fragments of the projectile that we hope we will find on the target. And from the that we have, and I collected directly from the chamber. It was not found in larger ankles, so to be inside the ejecta collector. So I assume they traveled very, how can I say, in very small ankle relevant to the impact angle. We will see. So both filters then, okay, how can I identify the fragments? Both filters, we scan them with the SEM, scanning electron microscope, and then we have raw light images of all the filter, and also in every field of view that we scanned, we also took some X-rays in every element. So we have the same field of view in different elements of the periodic table. I will show you immediately pictures, but this is a lot of data from the successful shocks. And so the question is, how can I proceed and analyze all this data? So up to now they used to do it by eye, just measure fragments, but that's not good. And it's the thing, it will take weeks and we don't have this time. So we put it, as I said, we took the maps, and because it's magnesium rich, it has a high signal on magnesium. And we know that from our gun, we don't have contamination in magnesium. So this is a frame, a light frame of backscatter from SEM. So you can see here, you cannot understand what is peridot, what is carbon, what is iron. Probably I can now after so many months, but generally you cannot. So you have to be sure what this is which. So this is a map, the same field of view magnesium, the same field of view in silica, and the same field of view in iron. So you can see why we choose magnesium, because for example silica and in iron we have, you understand, other features that are not, they don't belong to my projectile, although peridot has a combination of all these three elements. That's why we choose magnesium maps. Still, the fragments are too many. Okay, so I will run. So in order to find all these fragments and to have the distribution, we use a very sexy program, Sextractor, and we did actually, we thought, okay, we said, let's say, these are something like large forces. My background is almost zero. So what we will do? So we can apply astronomical photometry to find what we want, because Sextractor has a very nice, how can I say, command, so you can, instead of using, for example, the normal aperture, circular aperture in order to do photometry, we can use the ISO aperture. So the ISO aperture tries to identify the irregular shape of every fragment, so it's not a star. I don't want to lose pixels, so I want to have as many pixels as I get. So the result of Extractor is that it can give me the area, the flux, okay, but the area in pixels of every fragment, X and Y, allocation, ellipticity, which are the problematic fragments that I should not account in my distributions, and of course the number of fragments. So there are, this is size distribution. The y-axis, the longer axis, this is in microns, and this is the number of fragments. So it is very simple, and we expected something like this. There are two different colors, two different ways of which fragments I will count or not according to the flag that Extraction gives me. This is my scale, 0.5 microns per pixel. So I have, for now, good resolution to identify, but still we have to divide the population because we lose many fragments as we filter, and I think I have to see that even ISO takes all the effective area inside. So these are technical. So in order to conclude, we wanted also to test the final state of the big fragments of the projectile. So we took the big fragments that survived of the 1 and 2 kilometer source, and we put them in Raman, in lasers. So this is the shift in Raman, the spectrum in Raman from a specific laser, and here we can measure. So the blue is the reference, and the red is my real spectrum from my project. So this is from 1 kilometer per second, and here, if I compute the differences between the peaks of the two main peaks in Raman, we don't get large at least larger than the accuracy of Raman. But if we go 2 kilometers per second, is getting larger, this means that I lose iron from my surviving projectile, and probably it's something important. Up to now, as you can see, this is the red line is the reference, the number from the reference. The other points are the measurements of the difference of the two peaks from the big fragments that survive. And as you can see, also nothing exceeds the accuracy of the instrument. So we haven't detected so far escape of iron from the projectile, but it's something that is very interesting to see. So, my last slide, we wanted also to do a very fancy plot that all people do when they do these experiments. So, calculate the Q, the energy density at the time of the impact. So this is the formula. The formula actually is very simple. It's the kinetic energy of the projectile divided by the total mass of the system, so the target and the impactor. But in our case, because our target can be considered as infinite compared to our projectile, we have to remove it by magic from this equation. So then also we can remove the mass of the impactor is also removed. So you can see that Q is finally independent in this specific setup. I mean, independent from the mass or from which projectile I use, and it depends only on the impact velocity. So this is what I get. Unfortunately, so far I have only 4 good points. So my power law here that I try to fit, probably it will be better because we have to finish with the experiments. So in order to start to have catastrophic disruption, I need to preserve half of the mass of the projectile and less. So the red line here gives me this threshold. So when my model, my power law, my fitting, intersects with the red line, then I have the Q star, which is the Q, the density energy is about 200,000 something here, that I have for this. This is exactly a plot for this specific setup, ice and peridot. Future work. Try to change, for example, the peridot and fire with basalt, because basalt we can easily found in spheres, so I can try to have higher velocities, up to 5 or 6 kilometers per second, and repeat this job. Another thing that I was trying to do is to still use peridot, but change the target, not use ice, but another rock. In order to use a rock, you have to find a clever way to remove it and have only the mass that is a bed of the crater. So this is possible to do if we can find a good rock, very clean, very clear, like for example Islamic spar, that we can easily dissolve in nitric acid. This is something that I have done. We don't have residues, so we result only with the mass on the target. I tried to do something using limestone, but limestone is a natural rock. It has a lot of minerals, and still we don't know the exact composition if, for example, it contains magnesium. So it is something that does not contain magnesium, otherwise I cannot follow the procedure that I did. And the thing that I want to do from the beginning is actually to use real controls and fire them on ice or on Atlantic spar and see what's going on with more real materials. And I'm leaving you with a picture of my crater on the limestone that I tried to do as first experiment. Okay, I thank you very much.
Yes, time for only one or two maximum.
I'll have one. First, one comment. We have this equipment. It is polite to invite your old teacher to shoot. The thing is, eventually, in your experiment, did you manage to measure how much mass you transferred from the projectile on the target?
Okay. I expected that question and didn't have time to include this. Of course, that's my goal. So, why I didn't do it so far? Because I was paranoid. I want to use the cleanest water on earth for my target. So I bought from chemicals very nice bottles of very clean water, but this water was not so clean. So when you freeze it, because I used to freeze my target minus 140, the residues that it has inside, and didn't inform us about these residues, they create lumps only when you freeze it. I had 1 month this problem. I couldn't understand why I have contamination on my filter, why the ejector collector is clean and it was other type of water, and why my target that is a super clean water has this contamination. Actually, it has like a sludge. It has a layer of silicon on the top, which is something amorphous, and I cannot have good maps. I cannot measure my fragments. So I have the filters, but they are a bit useless now. Half of them, not all of them, to be honest. I have 2 salts that I'm still, they are in the microscope now, so that's why I couldn't have these results. So that was my problem. I had contamination, so I was trying in 1 month to do a lot of tests to understand from where I have this contamination. So it's a real crazy thing. Small things that when you freeze it, they create lumps. When you defrost it, and then even if you heat it, I heat it up to 50 degrees Celsius, they will never dissolve again back. In order to save my target.
So
that's why
you need to change the water.
it was